So this is slightly technical work today, and let's see. Well, so few general remarks I want to start with. So for cosmology, we really need to solve Einstein equations. So we need general relativity. The next nearest step is supergravity. Which one? Second, yeah. So some people, again, we agree to disagree, and in fact, I'll have a very specific statement at some point. I just gave this talk last week in Louvain, where all supergravity people were there, and so maybe I will answer later. It was a question which Paul Townsend asked me after, very close to that. So let me just postpone. But so for many people, depending on their background, this is a natural step. Now, however, we also want to stress that superstring theory is believed to be the most fundamental theory we know, but it doesn't have space-time immediately. You have to really make some steps from string theory, which is well defined on the world sheet, to space-time. And then you have to make certain approximations, and different people have different ideas about how exactly to do it. So what my talk will be saying that if these steps have some amount of supersymmetry, maximal or minimal or intermediate, if it is preserved, then we find consequences for cosmology which are potentially supportable or falsifiable by observation. And so this is kind of my point, that I'll give you assumption, prediction, and the future data will falsify them. That's the point. Now, obviously, I think we agree that what is interesting for fundamental physics, at least as far as we know, early universe inflation and current universe acceleration and dark energy. So the new things in supersymmetry were about fundamental role of non-linearly realized supersymmetry, which was discovered by Volkov and Akulov in '72. Volkov was my mentor, and therefore for me it is really important to tell you this story. And the story was that number of people at different years were studying this, and then there was a gap. And so what happened recently, because of cosmology, there was the first observation that if you want Starobinsky supergravity, then Volkov-Akulov setting is the best. And then immediately afterwards, we have realized if it works, if it is correct for Starobinsky, it is totally general. So if you can use this setup for cosmology, it is extremely useful. And then there were a number of people in older generation who worked out the details in the younger generation, and I may have not put everything, apologize. So the discovery of dark energy and observational success of early universe inflation associated with de Sitter or near de Sitter space support Volkov-Akulov non-linearly realized supersymmetry from the sky. And I'll make a stronger statement, where I will add the word arguably. But the fact that it is supported, in my mind, is clear. And this, by the way, is in contrast to a non-discovery of low energy linearly realized supersymmetry at LHC. So the story is that immediately after discovery of supergravity, Paul Townsend in '77 has written a version of a theory without scalars, which was ADS, and it was immediate and obvious. The moment you know supersymmetry, you have ADS supergravity, no scalars. It took a while, and just in 2015, to build DS supergravity, which has the DS minimum without scalars. Oh, sorry, I have to go back. Yeah, so this took a while, and this is the main topic of my talk. So this is just a reminder everybody has seen. Linear supersymmetry is typically associated with Zumino model. You have two scalars, two fermions, and they are partners. and there is a no-go for de Sitter in a simple case, and your cosmological constant is basically the value of W squared, and there is a minus sign, period. Now, meanwhile, nonlinear is much more complicated, and nobody cared for almost all the decades. And so the partner of one fermion state is two fermion state, etc. And an example of Volkov-Akulov action, it starts with some negative constant, and therefore, obviously, you see the source of positive energy. And then there are fermions, nonlinear. And so this was their action, and there is only a fermion in the multiplet. Now, local supergravity took a while, and so it was constructed just a couple years ago. And so we had our paper, and then next day there was a paper by Hasegawa Yamada, who is here, and he immediately became a postdoc at Stanford. And so the difference is that here, generically, your ADS has a negative cosmological constant, whereas here you have this extra f squared, which is positive, totally general, period. Now let's look at early universe and what we learned. And by the way, we spent $1 billion between the red and the blue. And so let's see what we learned. And my personal lesson was, back in 2004, it was one of our favorite inflationary models. We called it racetrack inflation in string theory with those two exponents. Worked very well. And it had this NS less than 0.95, which was perfect by 2010. But now it's just not there anymore. Not because of R. It has very low R. Just ruled out because of NS. Quite amazing. Now, our next favorite was in 2007. It was Disree D7 model in string theory, which, however, has NS 98. As you see, it was perfect in 2010, but not anymore, ruled out. What?
In order to make these statements about NS and small field inflation, you would need to know these Planck-suppressed corrections.
That is correct. So I take the model as a phenomenological model, assuming corrections are small, then I compare it with the data. Like with standard model. So standard model in particle physics, we have Glashow-Weinberg-Salam model, and the first approximation, it describes the data. And then we go in the weak coupling, we find small corrections, and this is for now my attitude. Right, so then there is an issue whether the corrections are small or not, and they are debatable. So for now, let me present what I know, and I'll continue. So in 2003, there was a KKLMMT model, which after a long set of investigation ended up with something which is known as inflection model. And with tiny exception, which I'll skip for now, the statement is NS is less than 93. So even in 2010, it was slightly marginal. Then there was an inflation model, which has R013. And now we are way below. So in short, I just give you examples. If I take the models by their face value prediction, they're all gone and not so much left. So let's see in more details what was special about the models which are still here, which we called alpha attractors. They have one parameter alpha, which is a curvature of the modular space, and they include Higgs and Starobinsky with alpha equals 1. And there was a funny observation in Planck that this model, which was developed in Appendix C of KKLMT paper, NS was 1 minus 5 over 3, 1 over n, and R is less than 10 to the minus 6. And Planck was saying it works perfectly, and I was very surprised, because I thought it is only an inflection point. So let me tell you the story. By the way, a string version of this is available for specific values of alpha equals 2 or 1/2, and this is known as fiber inflation by Quevedo et al. And so what is funny that this model can be validated by B-mode detection. if they detect B mode somewhere, we will know what alpha is. Whereas this one cannot be invalidated because NS is already in place, but during the next 2 decades, at best, we will know something for R above 10 to the minus 4, and this one has a very small R.
So it could be invalidated by a discovery of R.
Exactly, yeah. If it is discovered, it's gone. But if it is not discovered, it will stay and wait for, for 20 years. So therefore, what is interesting, so I couldn't understand why all of this. And then I looked into these famous Encyclopedia Inflationaris. They have 192 figures and 74 models. I still looked, so there is one figure, they call it KKLT inflation, and it sits precisely at 96 something and starts with 10 to the minus 6. So what they actually did, and so I couldn't understand, and then Andrea explained to me, just plot the model and compare it with alpha attractors. It's more or less the same. And because inflation takes place here, close to the shoulder, they both work very well for the data. So we are now working on supersymmetric version of this model, including volume stabilization, and we use something which we call geometric inflation, which I'll explain later. And so this is a model which is an appendix of our large paper, as well as their understanding of what KKL-TMMT is, according to number of French papers. And so this is quite surprising to me. Yeah.
Very honestly, are you suggesting that this is literally the potential that could be at that scale at which it would be? Like literally?
Well, so let me just, I'm trying to tell you my surprise. I'm opening Planck and it says, which are good models today? Alpha attractors I knew, but then they are saying that KKLMT is good. And I open Liam and Daniel review and it says it's inflection, which is NS equals 93. So, and now I know 93 is way out. So I start investigation, and because French people maybe somebody can.
I think it's just semantics. It's just because you have said it's inflection point with corrections, while they just write down the Coulomb potential.
Right, but if you have an explicit model that corrects it to inflection, then you have a very different prediction. So anyway, let me just continue.
Well, I think it's some of, let's see, K, other K,
Yeah.
M, and T would say that there's not a prediction for NS unless you do something like what these guys do.
Right. So
Which is to, establish what these corrections are in some example. And in their case, it was like 700 terms.
Right. So we are in the process of discussing this. And I just told you there is an open issue as to why this model. So what is amazing, that the model is literally sitting on alpha attractor plot. And therefore, it is not surprising. But of course, the condition why it works is a puzzle.
So we do not know yet how to make string theory.
Yeah, we don't have a string theory, but we do have a supergravity version.
At the moment when Maldacena have joined our team in investigation, this model which is right now in appendix C was the main part, and then he said it is ADS CFT, it's whatever, it must be
Yeah.
and suddenly the whole story completely changed.
Maybe we move it to discussion because, okay, one word, yeah.
This Coulomb potential is like Twali and Pi.
Yeah, except, I have a comment to that. Of course, they had it, and it was at the same time some other group, one had TH number next to it. But they never had at that time the concept of volume stabilization. So the one which the model which I refer to here has this Coulomb potential as well as the volume stabilization together, and it is supersymmetric. And what it means, we don't know yet, but it seems that those two models have the right NS by construction for reasons not yet quite clear, and so we would like to know more. So, and I want to explain that if I start with maximal supersymmetry and study B modes, whether I do M theory on particular G2 or superstring theory on particular compactification or directly n equals 8 and d equals 4, the simplest explanation goes from the fact that E77, which is a symmetry of scalars, has 7 Poincare disks, and therefore we came to conclusion that the most favorite targets which we have for 3 alpha are discrete, and they go from 1 to 7. And so there is at least one disk and no more than 7. And if I choose 55 e-foldings, I have a good NS. And these numbers scan the region for the satellite mission. And so this is another quote from Planck, which tells us in 2018 that for our models, they have computed the minimal value of alphas in different T and E models. And moreover, that because 2/3 alpha is the curvature, so they are computing the curvature, putting bounds on it, and that the discrete values, which I just mentioned, 1, 2, 3, up to 6, motivated by maximal supersymmetry, and we studied and we built cosmological model around this, and they're compatible with the current data and just sitting and waiting for satellite mission. So CMBS4 has this alpha attractor stripe here, and in the past the only known target was Higgs or Stravinsky at alpha equals 1. And so what I'm trying to say that now we have 7 different targets here, and I'm very interested to know whether they will discover B modes and when, at which R. So now I switch to, as I promised, very technical point. So first of all, when we deal with non-linearly realized supersymmetry, the no-go theorem are gone. And I already mentioned that this is the output, totally universal. You have always a positive contribution without scalars. You don't have to worry about Poloni, where people will tell me Poloni is not string theory. It's there, no scalars. So what we have, however, we have a nilpotent multiplet interacting with arbitrary chiral and vector multiplets with local non-linearly realized supersymmetry. And to prove it, it was necessary to change the known superconformal version underlying supergravity. And now we do have a very complicated, however, fully consistent theory. So what was known from 2003, that if you have a anti-D brane, it can do uplift for you, and a short version of it is to use the one nilpotent superfield, and this was known from 14. And just now, what we learned was that you can do anti-DP brane uplift. D3 is not special anymore, and this is what I try to tell you is technical, but very nice. So all you have to do is to take any anti-DP brane, wrap it on P-3 cycle whenever available, and each time you have an uplifter, and you end up with nilpotent superfield in supergravity action. And the situation is like D equals 4 supergravity always has F-term potential, many versions. Some of them can be recognized as coming from flux compactification on calibrated manifolds from D equals 10 supergravity, but some are not. Same here. But you have to have local sources, DP branes, and O-planes. The new thing which happened, that we can take any of these, and once we add anti-DP branes, we always have de Sitter supergravity and not the usual one. So before I go into details, I wanted to explain that during the last 2 years, we worked out something which we called anti-Disree brane-induced geometric inflation. And many of you have heard that not every scalar potential could come from supersymmetry. It has to be built from Keller and superpotential. Not anymore. So let me explain this. in this story, we work with the Keller function, which is a combination of Keller and superpotential. The potential is very simple, but the funny thing, the geometry of the nilpotent superfield allows you to introduce a function here, and you take it, roughly speaking, from the sky, and then you know what the supersymmetric version is. Very different from what it was before. And when we built it, I came across some notes of Eric Keller in 1933, where he told that once Hermitian Keller function is introduced, a long list of miracles occurs then. And so what we noticed in this cosmological model building, we even called it model building paradise, because you take any potential and you produce, under certain conditions, a supersymmetric version of it. That was unheard of. So when I explained this last week to Ferrara and Van Prooyen, and they told it cannot be. And I told, yes, we also thought so, but then between us, there was this code, model building paradise, but then we convinced ourselves it is working perfectly. We decided to keep this title in one of the sections of the papers. So let me go to this, instead of D3, so forget anti-D3, because anti-D3 you don't have to wrap on anything. But if you have anti-DP and you need a four-dimensional theory, you have to wrap it. So this is the picture due to Quevedo. But now I'll use it to tell you that de Sitter supergravity in 4 from flux compactification in D equals 10 will use those cycles. So, and this is the technical part. I try to be quick. So there are lectures on generalized complex geometry for physicists I'm using. There is a concept of calibrated DP branes, calibrated compactification manifold, and there is some set of Keller and superpotentials which involves Hitchin function and pure spinor polyforms. I'll skip it, I'll just flash for you. And you can use it for type 2A or type 2B. The important thing, they have to be globally defined, nowhere vanishing spinors. Once you have it, so the long story of string theory models, which people called full-fledged string theory models, boils down to the following, that you have to use SU3 cross SU3 structure, go from D equals 10 with specific fluxes, local sources, DP branes, and OQ planes, and then the dictionary gives you what kind of a Keller and superpotential you get according to every string theory model. That was a paradigm for a very long time. And I think everybody have seen the way it works in type 2A, and there are certain changes. So first of all, there are no-go, you can't do it. But then once you switch from Calabi-Yau, which is flat, to SU3 structure, and you add negative curvature, Eva a long time ago noticed that negative curvature always help stabilization. But here it is a principal point. But now we can add anti-D6 and keep n equals 1 non-linearly realized supersymmetry. So instead of going into rules, I'll show you one example. So when Tim Raze and I found the rules, same evening, he opened the old notebook, just added the new terms, and this is what happened. So without s equals 0, a number of people worked on it. I saw even Raphael was at that time involved. So people were running the codes, and their general conclusion was obstinate tachyons. They just couldn't get rid of tachyons in type 2A. And here they are. So the old story, everybody opens a code, and this is what they see. Same evening, we got the rules. Tim was running a code, and he got this. So I asked, let's do a slice. And in the slice, you have a maximum. Then you have an anti-D6 uplifter, and this is your new de Sitter. And this should, in your mind, be an analog of the picture where without, so this is the original story, it's anti-de Sitter minimum. Here it is de Sitter maximum, sorry, saddle point. Then you have the red uplifter, and you end up with de Sitter in both cases. That was kind of, he told, for a decade we were all running the codes. It never worked. There were always tachyons, and it just, the way it works, the new rules. So you have to add something which has a technical meaning of pseudo-calibrated anti-DP branes wrapped on supersymmetric cycles. Take all of them. Then accidentally, in type 2a, on calibrated manifold, there are no 5 and 1 cycles, but everybody else works. So here is the rule. Take everything you knew from before, add to superpotential a term with 1 nilpotent multiplet, add a Keller, and compute the green function, because we know the action. So the modification in presence of nilpotent multiplet and the fact that there is a non-linearly realized n equals 1 supersymmetry action was quite kind of surprising. It was important that this is nowhere vanishing, which is a consequence of those nowhere vanishing spinors. 5, 4, okay. So, and then we have to take into account all kind of conditions which are known. In the end, the new rules, roughly speaking, how the code has to be modified is computed in each case, because we know the action. And for type 2b, we have these 2 forms. For type 2a, we have a 3 form, and everything is computable. And here is the answer for type 2b. Those are new terms, the linear term in S in W and the quadratic in S, and it typically depends on the volume of a cycle on which the brane is wrapped. And this volume, one combination, was the tachyon. Not anymore. The same for type 2a. We have explicit answers. And so I'll conclude by saying that anti-Disree uplifter is not an exceptional case anymore, but it was the only one known to us in 15 years. For dark energy inflation, we need de Sitter or near de Sitter vacua. Now we found many more opportunities. Any pseudo-calibrated anti-DP brane, which upon wrapping supersymmetric cycle of dimension p minus 3 is an uplifter. And so in each case, string theory models resulting in de Sitter supergravity with non-linearly realized supersymmetry use any of such anti-DP branes. There is an issue with quantization of flux, etc., in these models, which has not been resolved because we just started. And so the non-perturbative string theory has Volkov-Akulov non-linearly realized supersymmetry on the world volume of its extended objects, on M branes and D branes, but not on the world sheet of the string. Therefore, it was difficult to find it. And here is the something with regard to Eva. So arguably, the discovery of dark energy and observational success of early universe inflation associated with de Sitter or nearly de Sitter spaces may be viewed as an experimental discovery of the Volkov-Akulov non-linearly realized supersymmetry from the sky. Exactly. So what Paul Townsend came to me and he asked, so why this is preferred to n equals 0, right? The perfectly valid question. And so in 2007 and 2008, when many people, Martucci, Marchesano, lots of string people, they studied, they gave the name pseudo-calibrated branes. And they knew that once they add to calibrated branes pseudo-calibrated branes, they can only get n equals 0, because in 2007, 2008, de Sitter supergravity with non-linearly realized supersymmetry was not known. Now, however, because we know that adding any anti-DP brane is a way with particularly computed scalar potential is a way to produce a perfectly consistent de Sitter supergravity, then we have a stabilizer in our models which allows us to build all kind of good models, potentially fitting the data. And there is an advantage of saying n equals 0, no rules. But if you have non-linearly realized n equals 1, it is, of course, a preferable option for some people, but not necessarily. So at least Townsend agreed with me.
No, it's not that there are no rules, and it's not a matter of opinion about what is generic, say, in string theory. You have to turn off a lot of stuff to get to the supersymmetric case. It may be the right answer, but
Right.
there's no observational evidence for it, even though there could have been at the LHC.
I would say I agree.
And it's not, it's just a fact that
It's
it's not generic in the theory.
Right. So the fact is.
The rules are, you know, the usual rules of physics, right? All physics that's ever been done, you
Okay.
don't have the rules of supersymmetry imposed, and it's, you know, controlled by perturbation theory or other clever methods that apply
Right.
without
So
supersymmetry.
I am trying to say the following. There is an option. And clearly, the situation with uplifters and the fact that we have to fit de Sitter or nearly de Sitter vacua is a natural possibility here. And it is in addition to a simple statement that n equals 0. I'm not against it. I'm saying we have a new situation which is very interesting. And for some people, it has an attraction. For some people, it doesn't. And then I leave you with that.